Okay, so again, let me just share the solutions. Again, you don't have enough to figure out what theta is. So we're not going to try and find theta. Okay, here we go. Okay, so we're here now. Okay, so again, we know that secant of theta is 7/4. We also know that secant of theta, right, is 1/cosine of theta. And I did actually show this in the lecture notes, not today, but I think it was the first or second day we did trig functions. But if 1/cosine is 7/4, to get cosine, you flip. So you get cosine of theta is equal to 4/7. I mean, you could cross multiply, then divide by 7, but you could just invert both sides, that is. So we get cosine of theta is 4/7. Now again, you want to have a right triangle where cosine of theta is 4/7. You want a right triangle where that happens. Well, how do we do that? Well, we know that cosine of theta is the length of the adjacent side divided by the length of the hypotenuse, right? We know that's true. So let's make the adjacent side of length 4 and let the hypotenuse have length 7. Again, we want a right triangle where where this is true. Cosine of theta is 4 divided by 7. So I'm going to take the adjacent side to have length 4 and the hypotenuse to have length 7. And we're roughly going to get this triangle. Okay, I drew the one above it as best I could. So using Microsoft Paint, I think I did. So here, this is theta. Cosine of this theta is adjacent 4 over the hypotenuse 7. Okay, yeah.
Where are you getting that the secant of theta is 4/7?
7/4.
Or 7/4.
That was given.
Oh, because the one you emailed was 5/3.
Oh, I'm sorry. I changed that. I messed up I emailed the wrong one then. I did change it here. It was 7/4. I'm sorry.
Oh, okay. Thank you.
You're welcome. I'm sorry about that. That was my fault. But secant 7/4. So, and again, secant is 1/cosine, right? So 1/cosine is 7/4. Then if you were to invert both sides, you get cosine is 4/7. So we have this triangle here, right? We made a triangle where cosine of theta is 4/7, right? If this is theta, cosine is 4/7. You know, adjacent over hypotenuse. But we don't know the length of the other side, right? This opposite side, OPP. How can we get it? Pythagorean's theorem. And that's what I'm doing down here. Pythagorean's theorem, right? We have OPP squared plus 4 squared must equal 7 squared. And now you just solve for OPP. You know, that's your unknown. You get OPP squared plus 4 squared is 7 squared. So we have our OPP squared plus 16 is 49. So then you just subtract 16, you get 33. So the unknown side, OPP squared is 33. So OPP itself is the square root of that. So in this triangle, we have this third side here has length square root of 33. And once you get that, you're basically home free because sine of that angle is opposite divided by hypotenuse. So it's sine of theta would be OPP, which we got to be radical 33 divided by 7. Cosine of theta we said is 4 over 7. Tangent of theta, that's opposite over adjacent. OPP over adjacent. And we found this to be radical 33. So we get radical 33 over 4. And then for the other ones, it's easy. Cosecant we know is 1 over sine. So you just invert this. Secant's 1 over cosine, that was given actually. Cotangent's 1 over tangent, which is this inverted. Okay? All right. I know that was a little tricky because I couldn't draw the stuff by hand, but I really hope everyone understood this. Are there any questions? Okay. And again, the one I emailed had secant of theta as, I think it was 5 over 3, but I meant to write 7 over 4. I'm sorry about that. That was my mistake. So what I'm going to do now is I'm going to start the next section, which is P5. Let me just get it loaded. I'm not going to go much into it today. Let me see. This can go here. Here we go. But again, there are more examples of trig stuff in the book. If you ever want to see me during office hours to go over an example like that, don't be afraid to ask me. I'll be happy to help you. Or if you're working on it and you need help, you can always email me. Okay? But if you don't approach me, there's nothing I can do. So, all right. No, I didn't share it. Let me share this now. There we go. So now we're going to go into section P5. Okay? I think it's section P5 from the book, but it's basically rational expressions. That's what we're going to look at. Okay? And what's nice about this is we already dealt with polynomials, so that makes the study here a little bit easier. But what are rational expressions? Well, you'll see what they are shortly. It's almost like a generalization of fractions. You know how from integers you can get fractions of integers? Basically, rational expressions you can get, essentially they're going to be fractions of polynomials. Okay? We'll see how to multiply and divide them and add and subtract them. Essentially, it's the same rules as for adding, subtracting, multiplying, and dividing fractions of integers. It's the same, like you need a common denominator, that kind of stuff. But a rational expression is just a quotient of two polynomials. You have one polynomial divided by another. That's all. So in other words, let me get the laser thing. So in other words, you have one polynomial P divided by another polynomial Q. That's what you have. So these are just some easy examples. You have 1 over x, 1 over x squared minus 1, x squared plus 4 over x to the 5th plus 3x to the 4 minus 2. That's all. So it's just fractions of polynomials. And again, since if you divide by 1, you're really not changing anything, any polynomial is itself a rational expression. Okay? That's what we get also. Now, just like for polynomials, I think we said this, although we said functions though, but you could actually consider the domain of a rational expression. You could actually do that. It's basically everywhere. It's everywhere the denominator is not 0. That's what it is by definition. That's what the domain of a rational expression is. The domain of it is all x such that the denominator is not 0. That's just, again, the definition. Okay? I mean, you could actually graph them as functions. Like we had polynomial expressions, then we went to polynomial functions. You could do that for rational expressions, but to graph them takes a lot more work, and we don't do that in this class. All right, we're actually out of time, so I got to stop.